Right now, we will learn some detail about the simple linear regression model. For the simple linear regression model, we have two variables, independent variable and dependent variable. We use y to represent the dependent variable, x represents the independent variable. Dependent variable is the variable we want to explain and predict. Independent variable is a variable that are used to predict or explain the dependent variable. So right now you can see the math formula for the simple linear regression. We have two variables, independent variable and the dependent variable. Except those two variables, we have other parameters. We have parameter beta 0, beta 1, and error term. Let's take a look at those parameters. First, let's take a look at the beta 1. It's also called slope. We have beta 0. It's called intercepts. We have the error term. Let's take a look at the slope. The slope, we use the beta 1 to represent it. So if the slope is positive, which means there is a positive relationship between the dependent variable and the independent variable. If x increase, y increase as well. If the slope is negative, there is a positive relationship between the dependent variable y and the independent variable x, which means if the x increase, y will decrease. The slope can be interpreted as a relationship between the two variables. Let's think about an example. If the slope equal to 2, when the value of x variable increase by 1, the value of y variable increase by 2. If the slope is equal to negative 1, when the value of x variable increase 1, the value of y will decrease 1. In the regression, the slope is very important in the equation. It's hard or solve for this equation because it will tell you how much you can expect the y when the x change. In general, the units for the slope are the units of the y variable based on the units of x variable. It's the ratio of the change in y per change in x. Except the slope, we have another variable, beta 0. We call it the intercept. So what is intercept? The intercept is the expected value of the dependent variable y when the independent variable equal to 0. If x sometimes equal to 0, the intercept is simply the expected value of y at that situation. But if x never equal to 0, this intercept, there's no meaning for the intercept because it doesn't tell you anything about the relationship between x and y. Let's go back here. Here we also have another parameter, is error. For this error, it will be normally distributed with the mean equal to 0. If the error is not normally distributed, we can probably, in this situation, we cannot use a simple linear regression. Let's go back to here. Suppose we have those data observation. we have dependent variable and independent variable. We generate a regression line for the data sets. We use the dark line to represent the regression line. And just try to compare a regression line to another line. So we use the dash line to represent other lines, try to fit this variable. When the x value equals to 0, the y value will be the intercepts. For this observation, it's observed value for this data point. But when we consider the estimated value, so there is a difference between the observed value and the S value. The difference we call it error. For the simple linear regression, we try to reduce the error to make the regression line fit most of the data sets. When we make a prediction, you may notice in the prediction formula, there is no error item because we just use the slope information and the intercept information to make estimation. Why we have error item in the regression line? Because dependent variable y can be driven by other factors. And in the formula, we just have the variable x, just one independent variable. Suppose let's think about the company sales can be driven by multiple factors like the advertising, like the product quality, like the price of this product. But when we make the regression, we only include the advertising costs. So for other two factors, like the price and the quality of the product, we didn't include those two factors in this regression, which means this variable just can explain this. The advertising cost just can explain the sales to some degree. So that's why we have the error. And when we make a prediction, we do not include the error. We will base on the slope and the intercept to make a prediction. When we use linear regression, we need to make sure the error item is normal distributed with mean error and the variance square. So you may notice for this regression line, and those data points, they are almost randomly located around this line. We use this line to represent their error. This error should be normal distributed. Otherwise, we cannot use the linear regression. Right now, let's take a look at the example. In this example, it shows the relationship. We try to find the relationship between the payroll and hours worked, and you can see this data sets. This data set is very short. We just have 11 observations. We have for the last years. It's a monthly data set. So we pull this data set to the R software. I will show how to use the R software to generate the linear regression line. Let's first take a look at this. We first plot the scatter plot for the payroll and the hours worked. You can see the x-axis is hours, the y-axis is payroll. You may notice those points, they are located, almost linear located. So we can draw a regression line around these data sets. Try to fit all those data sets. So this is a regression model. For this regression model, this is a formula. You can see the residual and you can see the coefficient. The most important civil information in the results is the intercept, slope, and the significance of the coefficient and how the model fits. In our example, we have the intercept is this one, and this is the slope. The p-value will show and this value will measure the probability that the value for the slope and the intercepts that are not derived by chance. But the p-value are not a measure of the goodness of the fit. We use r-squared or adjust r-squared to see whether the regression line perfectly fits the datasets. The r-squared and adjusted r-squared value are estimates of the goodness of fit the line. Then we present a percentage variance of the dataset explained by the fitted line. The closer the point to the line, the better the fit. In most cases, we will use the adjusted r-squared because the adjusted r-squared is not sensitive to the number points in this dataset. And the r-squared probably will influence by the number of observations in the datasets. So right now, let's take a look at how we calculated this in the R. Right now, I open R software. First, we try to upload the dataset to the R. We name the datasets, then read the datasets, use the read function, CSV. We use the function we discussed in the last lecture, the file, and press the enter button. It shows us we can choose the data sets. Let's take a look at the data sets. So here we have the payroll data sets. We just have 11 months. We have the payroll, we have the hours. First, let's find the value by the data hour, the hours. Right now, let's assign the hours to the x, which means the hours will be the independent variable. Let's take a look at the variable x. So it seems we successfully assigned the hours variable, the value in the hours variable to the x. Right now, let's assign the value of the payroll to the variable y. It will be the dependent variable in our linear regression model. Take a look at this variable. We have the value for the whole variable. It's a dependent variable. As I mentioned before we do the regression, we need to plot the scatter plots. Right now, let's plot the data set. We use this function called plot, and we enter the independent variable x, dependent variable y, press the button enter. It shows us the variable. It shows us the graph. So for this graph, we have the x-axis is hours, y-axis is payroll. So you may notice there the data sets, those data points that located is nearly linear. So we can, based on those information, we can use linear regression. So when we use a linear regression, so we assign this model to this one. We name the model and use the function LM, linear regression, and use Y, which means it's a dependent variable, and use X. Press the button enter to get some model, the simple linear regression model. For this model, so we regress Y on the variable X. We can see the summary. We can see the summary information for this model. It's almost the same as I showed you before. In this model, we have the intercepts, we have the slope. This is the intercept value, this is slope value. We have the p-value, and we have the fit, the goodness of the fit for this module. It's all the better. So if the adjusted R square close to 1, which means this module that is very good fit. It's perfectly, the regression line perfectly fits the data sets. If the adjusted R square close to 0, which means the regression line poorly almost didn't fit the data sets. So in our case, it's equal to 0.94, which means actually it's a good fit. On average, if we can get around the 0.5, it will be a good fit.